All right, so today's lesson, again, it's 215. It's the last one in Unit 2. It's called semi-log plots. This is like, it's weird, but it's not hard, I would say. It's weird because it's something you've never seen before, okay? This is not typically actually taught in pre-calc. This was one of those topics that got added in. And we're going to use a little bit calculator-based, and we're going to use a little bit without the calculator. So the first thing is like, what the heck is a semi-log plot? So if you look at the graphs on the left and the right, the left is your traditional. It's only quadrant one, but it's your traditional one, okay, where your X and Y values are equally spaced, or even if they're like changed, like you could go by 2s or 5s or whatever it is, you've got your regular spacing there. And then on the right, this is what's called a semi-log plot, okay? So it'll say semi-log plot or semi-log graph. They mean the same thing. But notice what's happening on your Y-axis. So on the x-axis, it would still be the same, kind of. We actually start this at 1 a lot of times. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, and so forth. You can start it at 0, but typically it starts at 1. And you can also change those intervals as long as they're consistent. So it can go by 2s, it can go by 5s, whatever it is. The x, okay, again, the x-axis doesn't change, okay? What does change is your y-axis. So what happens is it makes it in terms of log. And the benefit of a graph like this is it allows you to graph numbers that are like large, as like an exponential graph. So if I started with something small, like if you think about an exponential function, if I did 3 to the x, so let's just say, if I did 1, it's going to be at 3, which is it's a normal number to graph. Then it's going to jump to 9, then it's going to jump to 27, then it's going to jump to 81. So those numbers get bigger faster. And on a traditional graph, it's hard to graph those numbers. But on a semi-log plot, it makes it easier. So 1 through 10 are graphed as normal. Each one of those lines are 1 through 10. So this little guy would be 5, 6, 7, 8, and 9. Then it jumps to go by 10s. So then the next range from 10 to 100 goes by 10s. That would be 10, this would be 20, this would be 30, this would be 40, this would be 50, 60, 70, 80, 90, and 100. Then it goes from 100 to 1,000. So now you're going by hundreds. You're going by powers of 10. That's why it's called a log graph. So this becomes 200, 300, 400, 500, 600, 700, 800, and 900. Yep.
Is there a reason why it's so unevenly spaced?
No, I don't think so. What it does though, that spacing allows something to come when you graph exponential on a semi-log plot, it makes it linear. So the spacing is because of what's happening is basically you're going by logs on the left. And so the spacing is the same in each one, but it's smaller as it gets bigger, because if you kept raising it to a power, it would get bigger. The difference gets smaller. Does that make sense? Yeah, okay. You're welcome. All right, so when I plot this stuff, so we're going to plot these same values on the left and the right, okay? If I was going to plot this on my left axis, my x values are 1, 3, 4, 6, 8, so I could go by 2s if I wanted to. You can start. You can't start with 2 because then you wouldn't be able to plot 1. But if you start with 0 and you go to 2 and you go to 4 and you go to 6 and you go to 8 and you go to 10 and you go to 12. If I started with 1s, it would just go off, right? Because there's not 8 dots. On the left-hand side, I want to get all the way up to 900. It can go a little bit off your graph, but you don't want a bunch off your graph. So you could literally go by hundreds here. I could go 100, 200, 300, 400, 500, 600. Now I'm going to have to go off the graph a little bit, but only by 1 point. So then 110 is going to be literally just above your x-axis. 346 is about halfway. 498 is right under that first tick mark. 6205 is just above 200. 905 is going to obviously be like way up here. And that pattern clearly looks exponential. We don't have to connect them because it's not an actual graph, but that pattern clearly looks exponential on this. So on a regular graph, you're going to see that curve happen. We good so far? Now we're going to plot it on the semi-log plot. So 1, notice we started at 1 at the beginning. So 1 is at 10, which means I go all the way up here. 3 is at 46. So after the 10s, I'm going by 10s. So 3 and 20, 30, 46 would be midway between the 40 and the 50. 4 and 98 is just under the 100 mark. 6 and 205, right above the first one after the 100. And 8, 905, 8, 905 is here. Now notice that overall shape looks linear. If we were exactly accurate, it would be a perfect line. So notice that on the bottom I wrote it, but notice that what happens to the exponential when it graphs on a semi-log plot, it becomes linear. So the questions you'll get that I've seen on the AP exam practice stuff with semi-log plots are, 1, determine which graph is an accurate semi-log plot. And sometimes they'll adjust both the X's and the Y's, and that would obviously be wrong. Sometimes they make the X's go by 10s, 100s, and that is wrong. And then obviously you'll have your true one where the X's are going in even increments and the Y's are going by 10s, then 100s, by 1s, 10s, and 100s. And then the other thing you'll get, and you'll see this in the homework and you'll see this in example, is if I plot this data, which of these graphs is going to give me something exponential? And there are 2 ways to find a graph of an exponential. 1, your traditional graph, in which your curve is increasing exponentially. 2, a semi-log plot that has a linear pattern. Dane.
Why do you call it semi-log if it's mainly dealing with exponential?
Well, but the left-hand side, you're graphing an exponential, but the left-hand side is by log. And it's semi because it's not both, I think. That's why they call it. I'm going to look it up, but I assume that because the X is normal, but the Y is the one that's increased by logs. All right, so example 1 says, plot the data on the coordinate grid and on the semi-log plot. Is the data exponential? And if it is, find a regression equation for the data. So start by plotting your points, both exponential and then semi-log. Okay, so once you plot your points, you should get something similar to this. Again, it depends on how you do your spacing on the initial one, but it should look something like this. So is this exponential? Yes, if it asks you to describe why, you could either say on the given graph that points increase exponential pattern, but really the justification is that on the semi-log plot, it creates a linear pattern. Now, when it says to find the regression equation for the data, what kind of equation are we finding? Exponential. So we're going to enter in our points into our stat plot, and then we're going to find an exponential regression. All right, so I entered in the information into the stat plot, and then I'm going to create a regression that is exponential. So stat, go to exponential, which is 0. All right, so I got my regression 1.1165, so 1.117 times 2.234 to the x. Good so far. All right, then B says complete the table to find log of y and then find the linear regression of model x, comma y log. So what this means is I'm going to find the log of each of those y values, and I'll show you two ways to do it, one longer way and one shorter way. And then we're going to take the x and the log y to create a stat plot that would be linear. And then we'll create the linear model, okay? So first thing you could do is literally go through and hit log 8.2, log 17.5, log 97.2, log 39, whatever, and find them each individual, okay? But then you'd have to store them in your stat plot, so you'd have to retype them in. So a shorter way to do that is we're going to go to our home screen. Well, we're on our home screen. We're on our home screen, okay? We're going to log list 2. So, right, list 1 was our x values, list 2 was our y values. So we literally hit log. And then we can bring up our list on the list menu, which are above stat. So I do second stat, and I want to log list 2. That's the y values from my initial one. I'm going to close my parentheses because I not only want to do that, but I want to store those values. And to store, we go to store, arrow on the bottom, there. I'm going to hit store, and I want to store it in list 3. So I go stat, list. Oh, man, I think I didn't do something right. Hang on, we're going to see. Oh, no, it did. Okay. So now it took all that stat information, and it put it into list 3 for me. You see it? It's there. Do you want me to go through that again? We're good? Okay, do it again. So I'm going back to my stat menu, and I want to get a linear regression, so it's 4. And I want my x list to be y1, but I want my y list to be, good, L3. You literally go to list, so like it said L2, I go second stat to get the list, and I go to L3. We don't need to because it doesn't ask any questions from here. We could just go calculate, but if it did ask a question from there, now I would want to store it. So it is y equals 0.349x plus 0.479, and that's your linear regression.
Your x list is L1 or L2?
L1.
Okay.
0.7. It's 0.349 and then 0.48. Sorry, that should be 8. 0.048. Like an acrobatic act up here holding all this stuff and not also getting motion sickness. 0.48. There we go. Questions? Okay, so now here, because this is important, if I wanted to see a stat plot, like if I want to see the linear regression with the list 3, you have to turn on another stat plot, because our stat plot currently only has, like if you hit second stat plot, it's stat plot on is list 1 and list 2 only. So you can either change it there and make it list 1 and list 3, or you can add on another stat plot. It will be in a different color. And you can make it list 1 and list 3, okay? But you have to, if you wanted to see it, you don't have to see it for this, but if you wanted to see that linear regression, you'd have to turn on the stat plot with list 3. Does that make sense? Okay, Dane. All right, example 2 says use the data to find an exponential regression. So this time we're going straight to the stat plot. I'm entering in that data. Yep, you can hit clear on it. Remember, don't delete so because the list will go away, but hit clear on it. So in L1, 2, 4, 5, 8, 9. In L2, 7, 15, 23, 77, 115. And then stat, exponential. I'm not asking any questions about it, so I'm just going to calculate. I didn't even store it. Oh, because we did list 1, list 3.
You have to switch it back.
You have to, right? Go when you do linear regression, you got to change your y list back to L2. Y equals 3.083 times 1.494 to the x. Do we get it? Yes? You say no or you said yeah? Okay. All right. Then it said take the log of both sides of the equation to create a linear function. So there's two ways to get the linear function. The first is algebraically. So we're going to literally take our equation and we're going to log both sides of the equation. You don't really need to log the left as long as you understand what you're doing on the right-hand side. So this time if I log, so if I would get log of y equals log of 3.083 times 1.494 to the x, what do I do to expand the right side? That's a product, right? So this becomes log 3.083 plus log 1.494 to the x. Now log of 3.8 or 083 is just a number. It's a value. So we're going to literally find it. On our graph, what does that what would that be? Good. If I left it in exponential, that would be actually a translation, or if I left it in log, it would be a translation up, okay? But I want to make this linear. So what am I doing with the exponent?
Wait, what does it have to be linear?
You have to get rid of an exponent.
What's it have to be?
You got to put it to the front. So then log of 3.083 is 0.488, so 0.49, plus x times log of 1.494, which is 0.174. So if I actually wrote this in linear form, it would be like mx plus b, it would be 0.174x plus 0.489. Yeah. So this part of it is the linear part, but that's the method we took.
Can we just store the x value, the log of the x values in the list 3 and then
You can, because it's going to ask you to do this, but it's going to ask you, so that's two different parts. Like the first it says do it by finding the log. So you'll actually do the log of both sides. Then now it says find the log values and then find the regression, and then we're going to compare. So now I'm going to go back to my home screen and I want to log all my y values. So I'm going to do log list 2, store in list 3. So my calculator says log L2 arrow L3. And then I want a linear regression. So I'm going stat, calc, linear regression, and I'm changing my y list to L3. And calculate y equals 0.174 x plus 0.489. It might even be a little off, but it should be pretty close. We got it exact. It might be a little off when we round the logs on the beginning, but if not, it should be pretty close. Yeah.
So then why is the top one saying log of y and the bottom one just saying y?
This one you mean?
No, like
Oh, technically the linear I said like the log is there because that's what we did with it, but when you find it, it is just after the log. That would be your linear regression. So it says log both sides, you are logging the y, but technically by logging the y, you are changing the other side of the equation. So
When you do the linear regression, you gotta change it up.
you got to what?
Change it to L3
Correct.
for the y list.
For the y list, yep. All right, these should be fast. Good, because we're about to run out of time. Determine which graphs represent exponential functions and explain why. So which of these three are exponential, and how do you know it? The first one is, and why? So the semi-log plot results in linear with a linear function.
Make exponential linear.
Yeah. Is the second one exponential? No, it doesn't give, it's a regular plot, right? It's a regular rectangular graph, but my my y values are not increasing, so this is not. Is the second one, is the third one, sorry. Is this is a, what kind of graph? Semi-log plot, and it's exponential, so it is not. If it was a traditional graph and it had the exponential shape, then it would be. Does that make sense? So if these went by the same number, they were consistent, then that is a yes. And it's because your graph is exponential. Yeah.
But wouldn't the third one just mean that it's just going higher?
No, it literally means it would not be exponential. Yeah. So the change here, if it kept going that same change, then it would be. But these jumps are too big. Yeah.
So if it was regarding, regular coordinate plane,
Then it would have been yes, correct. All right, last one says the table of values for a function f at selected values of m. Which of the following could represent the data in a semi-log plot where the vertical axis is a logarithmically scaled? So this is literally how you could get a multiple choice question on your AP exam. And if you just understand what a semi-log plot is, this question should be easy. So look at your, first rule out anything that doesn't have any logs on the y-axis. That's that one, right? That one's not going by the logs. The other ones are, but now we need to look at the spacing of it.
First one, right?
B is definitely not. A, what's wrong with A? These are all equally spaced, and it's not going 10 and then 100. It went 50, so not. Go to C. Does C look good? Why not?
Because it's supposed to be one, not.
What's true about these values?
It's because for 2, it's 32.4. It shows like 2 at 10.
So just pick a point if you want. Do you have 1 and 18 on this graph? No, do you have 1 and 18 on this graph? Yes. Do you have 2 and 32 on this graph?
Wait, doesn't one in the middle of it though?
Wait, 1 where?
No, wait, yeah, no, it is.
1 and 18, sorry. Sorry.
The bottom is
This is 1. Is 1 and 18 on this graph? Yes. Is 2 these, right? It doesn't have to start with 1. I said it typically starts with 1. It doesn't have to start with 1. Yep. So what's the difference here, really? The x's are spaced differently, yes, but is that a problem? It's both. You're both right. These are spaced differently, is what Alba's saying, which is a problem. And what kind of shape does an exponential graph typically take when you put it on a semi-log plot? The linear.
just look at that and just be done.
The data has to be exponential for that to be true.
I was saying like the process of these, like the first one goes by 50, so it's not that.
Yeah, correct. You could look at your spacing, just your spacing alone. Yep.